All right, I think we will get things started. Totally fine if people come in a little bit late as well. But I just wanted to say thank you again, all of you, for being here. My name is Stephen Kissler. I am a new assistant professor in computer science and really excited to be here. I actually did my undergraduate and master's degree at CU Boulder, so I'm pretty familiar with it, but I've been away for a while. So I'm really excited to be back. And I'm excited to have the chance to share with all of you some of the work that I've been doing. Hopefully get you excited about infectious disease modeling, which is what I focus on right now. And hopefully get to the point where at the end of this talk, you'll both have a decent sense of what infectious disease modeling is, how the field developed, and maybe even being able to write down some models of your own to start thinking about the way diseases spread. So I think, without further ado, we will dive in. Let me pull up my slides. Great. So there is that. I'm going to reduce that window, and I will try to keep up the chat. So if anybody has questions, probably the most efficient way is to just unmute yourself and fire away. But I will also try to monitor the chat as much as I'm able. So if anything comes up, feel free to ask it in there too. Great. So as I mentioned, today we're going to be thinking about infectious disease modeling. My background is in applied mathematics. And so this will be, well, the talk will be mathematical in the sense that we'll be thinking about differential equations. We'll be thinking about how do you translate a biological system or a disease system into a mathematical model. Yeah, so that's sort of the direction that I focus on most of my research. The intersection of that with computer science, I think, is an interesting one because a lot of the data that we are now collecting for infectious diseases really requires these robust digital platforms, whether that's data on the pathogen itself or on human behavior, on the ways that people move and interact with each other. And so in infectious disease modeling, we think about all of those things. And we try to figure out the best way to collect those kinds of data and then to use things like simulation and inference to figure out what to do with those data to have a better sense of how to control infectious diseases. So today I'm going to give an introduction to the modeling that we do to get a better sense of how infectious diseases spread. Great. So we're going to start in a maybe unusual location. I'm going to start off with some history. And by history, I mean going back really far to try to get a sense of how we as humans have tried to conceptualize infectious diseases, really from the very beginnings of when we've been trying to conceptualize anything. And once we move through that, I'm going to introduce this object called a compartmental model. Compartmental models are basically the mathematical structures that we use probably 95% of the time to model infectious diseases. So we'll talk about compartmental models, we'll talk about what they are, how to build them, and then ultimately what they can tell us about the spread of infectious diseases. And then in the end, we're going to sort of do some special topics. So thinking about how do we make those compartmental models more realistic? And here's just a short list of a couple of things that we can do to tweak those compartmental models and make them reflect the situation on the ground a little bit more closely, and also make them more powerful so that we can make better inferences and make more and more detailed suggestions for what we should do for infectious disease policy. So I want to start by observing that humans and infectious diseases have been interacting with one another for a very, very long time. And for that whole time, we've been trying to make sense of what is going on. We can see this to some extent with the very word epidemic. So the word epidemic comes from Greek, from these two words put together, from epi and demos, which literally just means upon the people. So some of the earliest conceptions of infectious diseases were sort of this force that exerted itself upon groups of people. There wasn't a clear sense, of course, of where the epidemic, the thing that was happening to the people, was coming from, but there was a clear sense that epidemics came and went, that they would affect a certain group of people and not another one, maybe at different points in time, which is very different than other types of diseases that seemed to be sort of hanging around similar prevalence all the time. We can actually see some of the really, I think, ancient roots of our relationship with infectious diseases through some of the other words that we use to describe specific infectious diseases, like influenza, which comes from the Italian, previously the Latin, literally for influence, where the idea of where influenza came from was an astrological origin, that the influenza epidemics that would sweep through communities at the time had to do with the configuration of the stars. Similarly, malaria, which is a mosquito-borne illness, for a long time, we thought that malaria came from bad air that people were breathing. So literally, the term means bad air. So we can learn a lot about some of these early prototypes of what infectious disease is by literally just looking at the language that we use to describe infectious disease. Some of the earliest concrete descriptions of infectious diseases that we have comes from this gentleman, Hippocrates, who was around about 300 to 400 years BCE and wrote a couple of books. So he's considered to be the father of modern medicine. If you go into clinical medicine, for example, if you go to medical school, most of the time you will say the Hippocratic Oath, which has its roots in Hippocratic medicine, which was sort of this man was the forefather of. But in addition to thinking about regular clinical medicine as we think of it today, he also thought an awful lot about epidemics and wrote a couple of books talking about the various symptoms that people would feel as a disease would spread through the population. And in these books, we have some of the earliest descriptions of diseases that we know today as cholera, as influenza, some sexually transmitted diseases that are still circulating today were described in the book as well. And so it's very clear that some of the very same pathogens that are still causing problems today were causing problems way back then, and we were trying to conceptualize them in a rigorous, almost scientific way. I'm going to step through a history of a couple of infectious disease pandemics, because I think that in addition to learning about the pandemics themselves, what I really want to focus on is what thinking about how we responded to these pandemics in sort of an intellectual manner can tell us about how mathematical epidemiology evolved over time. So in the 500s, this is now many centuries after Hippocrates was around, we start to see accounts of what's now called the plague of Justinian. We think it was probably bubonic plague, which is generally spread by rats and is a really, really nasty disease. And this picture is a woodcut of an artist's rendering of the scene at the time. And really what I want to emphasize from this is just the utter chaos that we see in this image. And so I think that this gives us some insight into the way that people were conceptualizing infectious disease transmission at the time as this lethal, chaotic, in some ways impossible to understand kind of thing. I want to contrast this with an epidemic of probably the very same pathogen, but some hundreds of years later. Now, this is another woodcut with the theme of the Danse Macabre, which is a very common theme around this time, in large part because the Black Death had such an impact on mortality during that time period. Now, one could question whether this is a step forward in our conceptual understanding of infectious disease transmission, but I think that it really is if we take a close look at this, because what we're starting to do is we're starting to generalize and sort of abstract our understanding of infectious disease, now not as sick people running around a community, but as these dancing skeletons. And actually encapsulated in this figure, I think, is a quasi-scientific understanding of what was actually happening for the cause of the Black Death at the time. So the belief at the time was that the Black Death was caused literally by the bodies of people who had died from the previous plague sort of emitting these fumes, causing bad air and infecting people. So you see this image of a skeleton rising up out of the grave, sort of mimicking this almost scientific idea of where the plague was coming from. And then over the top of that, we see these skeletons dancing, which is suggesting this sort of odd kind of order to this plague that was spreading at the time, which again is sort of contrasts with the chaos that we saw previously. Now, if we move a little bit forward, yet again, a plague is spreading through London, but we fast forwarded another couple of centuries, 1665 and 1666. Here, we really start to see some rigorous and almost mathematical understanding of the spread of disease. I want to highlight this book, The Journal of the Plague Year, which was by Daniel Defoe, same person who wrote Treasure Island. And in this book, he gives essentially a first-person account of the Great Plague of London. Now, it turns out that this is actually not his own first-person account. It's a first-person account that he is telling through the eyes of his uncle, who actually lived through the plague. So it sort of sits on the line of fiction and documentary. But one of the things that I want to highlight is that in this book, we actually start to see tables of statistics measuring the number of people who died from the plague and the number of people who exhibited different types of symptoms. And I think that this was a really important innovation because by tabulating these kinds of numbers, this gives us a backbone to use when we start to build mathematical models. Another thing I want to mention about this is something from the conclusion. So in the conclusion of the book, the plague starts to abate, but it's not because everybody has gotten it. I've highlighted this section from the end, which says that the circumstances of the deliverance were indeed very remarkable. The contagion despised all medicine, death raged in every corner, and if it had gone on as it did then, a few weeks more would have cleared the town of all and everything that had a soul. In that very moment, we might well have said, vain is the hope of man. I say in that moment, it pleased God with the most agreeable surprise to cause the fury to abate even of itself. It was wonderful, even the physicians themselves were surprised at it. Nor was it by any new medicine found out or new method of cure discovered. Basically, no account could be given of it. The reason I bring this up is that this very phenomenon, the fact that an infectious disease can turn around before everyone has been infected, that it can sort of spontaneously leave in the same way that it seems to spontaneously arrive, was a real mystery. And in fact, it was the central mystery that was behind one of the first mathematical models that was written down, and the one that sort of provides us with the framework of mathematical models that we use today for modeling infectious diseases. So now we're moving forward towards a more mathematical understanding of infectious diseases. Many of you will recognize this gentleman, Daniel Bernoulli. The Bernoulli family was responsible for writing down a lot of the mathematics and physics that we're still unpacking today. And it's no different with infectious disease models. So in the 1700s, Daniel Bernoulli was tasked with this question of trying to understand what would happen to the average life expectancy in Paris if we were to variolate against smallpox. And variolation is a precursor to vaccination, but basically it's the same idea where you introduce some previously infectious biological material into a small abrasion on a person's skin, and that creates a localized immune response that usually is not particularly dangerous to their health, but then ramps up their immune system, causes it to learn what smallpox looks like, and then protects them from infection in the future. And so Bernoulli's question was, how much longer will people live if smallpox is eliminated? And to answer this question, he wrote down a mathematical model. Really, this was the first compartmental mathematical model of infectious disease transmission. And it was in this treatise from the 1700s. And essentially, he conceptualized that people could exist in one of two states. Either they were susceptible to smallpox or they were immune to it. And you can move from the susceptible to the immune state by either getting infected or through variolation. And then you can leave both the susceptible and the immune state by dying. And so this mu captures mortality, sort of the baseline rate of mortality. And then this additional rate along the bottom here is basically the probability that you contract smallpox and die from it. So the question is, if we can port people from the susceptible category to the immune category through variolation, how many lives will we save? And so this was one of the first successful attempts to use a mathematical infectious disease transmission model to advocate for policy change. Now, this was a really important step forward, but before sort of it could really blossom, there were a couple of steps that were needed first. And these were really in the realm of infectious disease statistics. One of the pioneers in this area was Florence Nightingale, who was both a field nurse and also an incredibly talented statistician. So in a lot of her work, she was interested in understanding how deaths in field hospitals were changing over the course of a year. So she generated these very sophisticated types of data visualizations. They're sort of like pie charts, but actually sort of give more of a sense of the time course of infectious disease transmission and all-cause mortality over time. So each wedge here represents a month of the year, and each color in the wedge represents different causes of mortality. The shaded gray regions are infectious causes of mortality, and you can actually see here effectively an epidemic unfolding where these wedges are really getting larger and larger, and then they abate again. And so by collecting data and then visualizing it, Nightingale was able to advocate for health reform and especially to advocate for sanitary reform across many different regions of the world, in fact. And so by translating the data like was tabulated in that in Daniel Defoe's novel, like I mentioned, by tabulating that and bringing that into a visualization, she was able to make much more sense of the data and to make a much more compelling narrative about what should be done with it. Similarly, this gentleman, John Snow, was a physician in the 1800s and was interested in a major cholera outbreak that was happening at the time. And to try to get control of it, he took a slightly different data visualization approach and just marked down on a map the locations where people who had contracted cholera lived. And in doing so, was able to show that most of the cholera cases in this area were all centered around a single water pump, where presumably people were drawing their water from. Now, at the time, it wasn't completely clear where cholera came from. There was still a sense of this miasma or bad air theory. But by generating this map, John Snow was able to essentially demonstrate with a very high degree of evidence that cholera was waterborne, that it was coming from this pump, and that by restricting access to the pump, it would help to reduce the outbreak, which in fact happened. So now we're finally getting into the forefathers of contemporary infectious disease models. And so I'm going to spend a little bit of time on these two and the ideas that they came up with, Kermick and McKendrick. So the question that I had mentioned earlier from Daniel Defoe's novel, The Journal of the Plague Year, was the same one that was bothering these two. Why do outbreaks end without any clear reason? There's no clear change in behavior. It's clear that not everyone has become infected, and yet an epidemic can die away. And why is that? Well, to answer that question, these two decided to write down a set of equations. And it turns out that these equations are today the fundamental equations of infectious disease modeling. So these equations are to infectious disease modeling a lot like the laws of Newtonian mechanics are F equals ma, or Maxwell's equations are to electromagnetism. These equations sort of occupy the same status in infectious disease modeling as those do in their respective fields of physics. And the equations look like this. They're pretty straightforward, but they can get a lot more complex very quickly. So they were first put forth in this 1927 paper, A Contribution to the Mathematical Theory of Epidemics. And we're going to break these down over the next couple of slides. Before we do that, I want to talk a little bit about compartmental models. So in a compartmental model, we usually think of different buckets. Each compartment represents a bucket that can be filled with a certain amount of stuff. And so I like to think about compartmental models as buckets that have water in them, and that water can move from one bucket to the next through these hoses. So here we have a bucket X, bucket Y, bucket Z, and we can characterize the amount of liquid in each of these things using a differential equation. These differential equations, the amount of stuff in X per time, or in Y per time, or in Z per time, is simply equal to the rate out plus the rate in. So that's what's represented here. So to make things concrete, I'm going to actually put some numbers to this. So there's a pretty thick hose on the first bucket. So I'm going to say the rate out is 3 times X times the amount that's in that bucket. And so that same rate out of X is going to go into Y. Then there's a thinner hose coming out of Y. So I'm going to say that the rate out is somewhat smaller, 1 times Y. And then the rate out of Y is just going to go into Z and fill up Z. So one of our jobs as mathematicians is to take this rate-based description of these compartments and to use it to make a description of what's happening with the overall volume of water in each of these buckets at a given point in time. So we can solve these equations by integrating them, and effectively we get this. So we have water flowing from x into y, so the initial volume in y increases, and water is flowing out more slowly from y, and so it decreases a bit more slowly. And we can plot the volume of water in x, y, and z over time with these three different plots, each of which looks a little bit different. Now, the very same idea can be applied to infectious disease models, where now, instead of buckets, we think about different epidemiological states that a person can be in. So a person can begin as susceptible to a given disease, and then upon infection, they become infectious with that disease. And then after a certain amount of time, their immune system kicks in and then they recover. So they essentially move from the susceptible bucket to the infectious bucket to the recovered bucket. And our interest is in understanding how many people are in each of these epidemiological states over time. So one way we can get at that is by writing out a narrative description of the situation at hand. So this block of text comes from the beginning of that 1927 paper, and we're going to break it down and translate it into mathematical format. So the problem may be summarized as followed. One or more infected person. So we're going to represent this infected bucket with an I, and our initial condition for that I is going to be 1. So one infected person is introduced into a community of individuals who are more or less susceptible to the disease in question. So we're going to represent our susceptible bucket with an S, and the susceptible population, this S sub 0, is roughly equal to the population size. The disease then spreads from the affected to the unaffected by contact infection. So that means that we have basically a pipe that allows people to move from susceptible to infectious. Each infected person runs through the course of their sickness and finally is removed, or they're recovered, from the number of those who are sick by recovery or death. So we're going to count the number of people who are recovered or who die from infection with this R category. The chances that the affected may convey infection to the unaffected are dependent upon the stage of the sickness. That's basically already captured in this model. As the epidemic spreads, the number of unaffected members in the community becomes reduced. So remember, unaffected here means susceptible. And so essentially what this is saying is, just like our bucket situation on the previous slide, people are going to move out of the susceptible state through the infectious state into the recovered one. Now, since the course of an epidemic is short compared with the life of an individual, we're going to assume that the population size is constant. And so we're going to say that the number of people in S plus the number of people in I plus the number of people in R is equal to N, which is our population size. So everybody in the population is in one of these compartments, and only one compartment. And so there's nobody that we haven't accounted for here. And then in the course of time, the epidemic may come to an end. And they say that one of the most important problems in epidemiology is to ascertain whether this termination happens only when no susceptible individuals are left. So have we emptied the S bucket, or whether the interplay of various factors of infectivity, recovery, mortality, and so on may result in the termination while there are still susceptible individuals left in the population. So that's the question that they're trying to answer with this model. So what do we do? Okay, well, I've just represented that model along the top of the slide here again, and we can translate this visual description of the model into a set of differential equations, just like the buckets of water that we saw on an earlier slide. So again, we're going to characterize the change in susceptible people over time by a rate out of the susceptible compartment multiplied by the number of people who are in it. Those people who leave the susceptible compartment are going to go into the infectious compartment, and then we're going to subtract the rate out of the infectious compartment. And then those people who leave the infectious compartment are going to go into the recovered compartment, and then they're going to stay there for all time. So let's take a look at what these rates need to be. So I've just moved that rate out times S up, and I'm going to put in its place a slightly more complex equation. So we can say that the rate out of the susceptible category is equal to the infectiousness of the disease, because we know that different diseases have different infectiousness. The infectiousness of COVID is different than the infectiousness of flu, which is different than the infectiousness of HIV. And we want to multiply that infectiousness by the probability that a susceptible person comes into contact with an infectious person. So that's our rate out. We're just going to translate these things into Greek letters to make the notation a little bit more concrete. So beta is our infectiousness. I over n is the probability that a susceptible person comes into contact with an infectious person, and we're just multiplying by the compartment size S. So we're going to take that same thing that's coming out of S and stick it into I, this beta in times S, and then we're just going to say that at a certain rate gamma, you can recover from the infection. So gamma basically tells you how long it takes for your immune system to kick in and make it so that you're no longer infectious to other people. And then gamma I is just put directly into that recovered state. And so people who move into recovered stay there for all time. So what kinds of numbers of people in each of these compartments happen over time? Well, the model looks something like this. So here's a video where I'm taking the infectiousness parameter, and I'll play this a couple of times. I'm taking the infectiousness parameter beta and increasing it. So we're moving from an infection that's not particularly infectious to a disease that's pretty infectious. Gamma here is 1, so the recovery rate is 1. So if we think about time, say in weeks, then maybe the recovery time is 1 week, and then the infectiousness ranges from 1 to 3 in these sort of arbitrary units. And what we see here is that even with this very infectious disease, in black, we have the number of susceptible people over time. In red, we have the number of infectious people over time. And in blue, we have the people recovered over time. We've scaled things so that the population just sits on a scale of 0 to 1. And what we can see here is that even with this fairly high infectiousness, the number of susceptible people in the population does not, in fact, go all the way to 0. In fact, it plateaus at some value slightly higher. So the idea here is that at some point, enough people in the population will have been recovered that they effectively act as a buffer against infection for the people who still remain susceptible. And so at some point, a susceptible people who's walking around in their community is going to have such a low probability of running into another infectious person because they're surrounded by so many other people who are immune that they're not going to get infected and they will stay susceptible. And so there's nothing inherent about this person's behavior that made them not get infected. There's nothing that says that the infection didn't need to spread to everyone, but it just sort of emerges out of these very simple dynamics. But we don't need to stop there. With this framework of differential equations, we can actually answer a lot of very important questions, including, will an outbreak happen at all? And if so, under which conditions? So one thing we can do is we can look at these equations and ask, well, okay, if an outbreak is going to happen, that suggests that there needs to be an initial increase in the number of infected people. Okay, let's translate that into math speak. If that's the case, then di dt, the change in the number of infected people over time, has to be 0 at the beginning of the epidemic. Okay, so when does this happen? Well, this happens when di dt, we'll just paste that stuff in, is greater than 0. I'll just bring that gamma I to the other side, and then we can note that our initial population size, the initial number of susceptible people in the population, is very close to the total population size. Because if you remember, we started off with just 1 infectious person, everybody else in the susceptible category. So it's a pretty good approximation to say that we can cancel S and N. We can cancel I from both sides of the equation. And so as long as the infectiousness is greater than the recovery rate, we'll get an epidemic. Or similarly, we can just pull the gamma over to the other side and say if beta over gamma is greater than 1, then we have an outbreak. Now, it turns out that this is really important because what beta over gamma represents is the average number of infections that are caused by 1 infectious person. I'll say that again. If we divide infectiousness by the rate of recovery, we're essentially saying how many people is an infectious person going to infect during the duration of their infection. It turns out this is an incredibly important quantity. This is the reproduction number, or the R number, which many of you will have probably become familiar with during the COVID pandemic. Keeping the R number, the reproduction number, under 1 is of critical importance if we want to keep control of an epidemic. And if the reproduction number is less than 1, then we won't get an epidemic in the first place. So how do we get the reproduction number less than 1? Well, there are a couple of different ways to do it, and it's harder for some pathogens than for others. Here's just a quick table pulled from Wikipedia of the estimated reproduction numbers for different infections. We can see at the very top that measles is just ragingly infectious. A person infected with measles will often transmit to 12 to 18 other people. For SARS-CoV-2, at least for the Omicron variant, we think that that number is probably somewhere between 6 and 9. So it's up there on this list. Whereas for the original SARS, we see 2 to 5. Influenza is actually quite low on this, 2 to 3, and Ebola 1.5 to 2.5. Of course, all of these are above 1 because they need to be, or else there wouldn't be problems. But clearly, even in that range above 1, there's a huge range across infections of how contagious they can be. Okay, so with this in mind, how do we reduce that number to below 1? In other words, what proportion of people do we need to vaccinate to ensure that there's no epidemic? This is very similar to the question that Bernoulli was solving all those years ago to try to understand how many people needed to be variolated against smallpox to increase the life expectancy. Okay, so how do we answer this? Well, we start in a very similar spot. If there's going to be no epidemic, then we just switch the sign of the inequality. We say di dt has to be less than 0 at the beginning of the outbreak. Okay, so we'll just plug in di dt for that, bring gamma I to the other side, and now here's where the difference comes in. I'm going to substitute something in very special for S. Earlier, we just said that S, the number of susceptible people at the beginning of the epidemic, was effectively just the population size. But now we have the opportunity to vaccinate people prior to the start of the epidemic. We vaccinate a proportion P of those people. So now, rather than N being susceptible at the beginning, we have a proportion 1 minus P times N being susceptible. So this basically captures all the people who didn't get vaccinated. And now we can simplify the equation again. The N's cancel, the I's cancel. We have beta over gamma has to be less than this quantity, 1 over 1 minus P. And if we remember, this beta over gamma was our reproduction number from before. So as long as the reproduction number is smaller than 1 over 1 minus P, we're good. What's more useful to rearrange this and say that P, the number of people we vaccinate, has to be greater than 1 over 1 minus R naught. So what does this look like? Well, we can plot this quantity, 1 minus 1 over R naught, and that's this curved line here. So on the horizontal axis, we have the reproduction number, R naught. The vertical axis, we have the number of people that we need to vaccinate to make it so that a disease with that infectiousness doesn't take off. And so we can look at what happens with a handful of different types of pathogens that we know of. So for the original SARS-CoV-2, we thought that the reproduction number was around 3. So if we take this reproduction number of 3, follow it up to the line, we can read off that we need about 66% of the population vaccinated in order to stop an epidemic from happening. We can do the same sort of thing with smallpox, which has a reproduction number around 5, for which we would need about 80% of the population to be immune to prevent an epidemic from happening. This SARS-CoV-2 Omicron is a pretty good description of why we were talking about herd immunity early in the COVID pandemic and why we are no longer. Part of that is because we need 87% of people to be fully immune against SARS-CoV-2 Omicron to prevent outbreaks from happening. Now, we've got nearly that many people vaccinated in many countries around the world, but the problem is that the vaccines aren't 100% effective. And so the effective number of people who are protected by the vaccine is somewhat lower. And we're probably never going to reach that 87%. There are other reasons too why herd immunity is sort of out of reach for SARS-CoV-2, but I won't go into that right now. And then we have the big bad one, measles, where measles is so contagious that you need on the order of 95% of the population to be vaccinated to keep outbreaks from happening. And we're seeing the consequences of this now, where there are a number of communities around, well, let's say, start with just the United States, where measles has been eliminated for many, many years because we've had such high vaccination rates in young kids, well beyond that 94%. But now there are communities where vaccination rates are dipping below that 94, 95%. And as soon as that happens, you can get an outbreak. And so this is one of the really important points of needing really high levels of vaccination to protect a community, especially against something that is contagious as measles. Okay, so we're rounding things out here. In a compartmental model, you can be in one and only one state. But the cool thing is that the states that you choose can be as detailed as you like. So we've been focusing on susceptible, infectious, and recovered. But there's nothing that constrains us from thinking in much more complicated ways. So one step forward might be asking, what happens if there's an incubation period? So what happens if you get infected, but you don't immediately reach a point where you're spreading infection to others, or there's a bit of a lag where it takes the pathogen to sort of increase in your body before you can spread it to other people? And it turns out if we do this, we can already start to get very different types of dynamics out. So in this plot, we have time on the horizontal axis, the number of people in the infectious category on the vertical axis. And we can see that with a regular SIR type model, without the incubation period, we get these much more sort of punctuated, spiky outbreaks. Whereas if you introduce an incubation period, even if it's very short, you can really spread out the number of infections over time. We can also ask questions about like what happens if you lose immunity. This is another thing that has sort of prevented us from getting to the point of having herd immunity for SARS-CoV-2, because even if you do become immune for a period of time, you can still very much become infected again and again. And when that happens, and we generate some equations and simulate from them, we see some very different types of dynamics over time, where here, rather than going back to roughly 0 infections, we actually reach a steady state where there's a certain number of infections that are sustained in the population over a long period of time. This is what we talk about when we talk about an infectious disease becoming endemic in a population. We can think about age structures. So we might have an SEIR type model, just like we had before, and now have one that pertains to 2 different age groups, where infections in one age group can transmit to another and vice versa. We can think about geography. So here's a map from some work that I did a couple of years ago on the 2009 H1N1 flu pandemic. Here, each disk represents a city in the United States, and the darkness of the disk represents how much influenza was spreading in that location at a given time. One of the really cool things that we see about this map is that there's this very clear sort of ripple-like transmission out of the southeastern United States, which we're still sort of puzzling over, trying to understand why that happened, why there was such a clear wave of transmission. And so one of the things we can do is we can take these compartmental models and run a compartmental model inside each of these cities. And then we link infections across cities based on how people move between them. We can get these very complex sorts of geographic dynamics of infectious disease that help us to anticipate where a disease will spread and when. And then here again is another example of a compartmental model with many more compartments to describe the spread of Ebola. So here what they were trying to do is to fit Ebola cases to data that were available from West Africa in 2014. And here you can see that susceptible people move to 2 different types of exposure, whether they're exposed in their community or exposed in the hospital, where they have 2 different rates of acquiring disease. Then they become infectious, and then you can either be hospitalized or you can recover without hospitalization. You can also die from infection. And then it's also important where they capture the burial state, because you can still transmit Ebola even after death, because the disease can still be spread through basically the caretaking that is needed to prepare a body for burial, which is pretty wild. And that can create these very different types of infectious disease dynamics that are important to keep track of. The last thing I want to point out is that we can use these models to think not just about the transmission of disease, but actually the evolution of pathogens themselves. And this is an area that is, I think, super interesting and what I'm very interested in. So here's just a model where we're tracking people moving from a susceptible state to an infected state to a state where they're being treated by antibiotics. And now each of these infected states represents, it's basically indexing their susceptibility to one or both antibiotics. So this is pretty cool because we can actually see not just do people get infected, but what types of strains do they get infected with, and how likely is that we're going to be able to treat them, and how long are our treatments going to last at the population level. And then we can ask, sort of the upper level question of once you get these antibiotic resistant strains, can they coexist? Do we have an endemic level of susceptible and resistant strains or not? And if so, how do we make sense of that? Why is it that one doesn't outcompete the other? So we can sort of nest these more and more complex questions using more and more complex models that are all sort of based off of this very basic SIR type compartmental model that we all learned about already. So just some final thoughts before I field some questions here. Compartmental models are simple, conceptually speaking, but they can be incredibly powerful. The question that you have in mind really determines the form of the model that you want to write down. So by thinking about all of these more complex questions that we have, like how do we prevent the spread of an Ebola epidemic, or how do we reduce the rates at which antibiotic resistance emerges in a population? You need to build a model that can sort of meet that question where it is. But once you do that, you have this very sort of mathematically incredible system to work with, and something that can be incredibly valuable for policymaking. And so it's important to understand the narrative first. It's important to understand your biological system and the question you're trying to answer, and then to use mathematics as a way to sort of come back to that narrative, answer it, and provide a clear way forward for controlling the spread of disease. So these are the sorts of questions that my lab is interested in working on. I'd be really excited to talk with all of you, both about your experience with infectious diseases, some of the things you're interested in studying, and just what other kinds of questions you have about this kind of work. So thanks very much for your attention, and I think I'll close off the slides and open it up to questions for a few minutes. Feel free to unmute, stick something in the chat, or just tell a joke and tell a story. The sheep in the background, it's a good question. So these are not drawn by me, but they are, I think that it was for one of the other faculty members was describing to one of the other faculty members' kids how to draw a sheep. So this is a step-by-step tutorial in sheep drawing. It's not totally irrelevant. I'm actually also interested in agricultural infectious diseases, and sheep are actually a pretty big culprit for many of those. So it's not entirely off the wall, but it is on the wall. And yeah, that's what they represent. Oh, any others?
Yeah, when it comes to
Oh, I just lost you. I heard you, and then it went mute.
How's about this?
Yeah, that's great. Thanks.
Is your lab more focused on like trying to create specific models for these diseases, or are you more interested in kind of tweaking existing models and running simulations to kind of see how they interact with the world?
So we're very much into model building. So sometimes there's a model that you can pull off the shelf that is that works for your purposes, but for most of the questions that we ask, you really need to either sort of, you're never starting from scratch. Like there's always some sort of background that you're building off of, but for most questions, you sort of need a fit to purpose model to answer it appropriately. And so, yeah, really, I mean, I think that we're interested in infectious diseases, sort of the broad category is just like pandemic preparedness. And so a lot of it is, a lot of what we use models for is for essentially trying to think about like, what is the scope of possibilities? If we assume certain things about how a given disease might spread and how people might respond to it, just what could happen. And models are a really powerful way of sort of interrogating that, of sort of thinking about what different future scenarios could be. And so that's one of the big areas that we work in. But usually the models are sort of things we build and code up ourselves.
Gotcha. Thanks.
Yep. Cool. Any others?
Hello.
Aha. Hello.
Hi. Yeah,
Yeah,
I'm
go ahead.
audible. Yeah, so I wanted to ask, what drove your passion towards this field? Was it related to the COVID outbreak? And did you note the efficacy of these models in stopping the spread or providing any forms of alleviation?
Yeah, thanks. So yeah, I like to say that I've been working on infectious diseases since before they were cool. So basically I've been doing research with infectious diseases for about the past 10 or 11 years or so. And so a lot of it was actually spurred from the original SARS epidemic. And there were some concerns around a bird flu pandemic crossing over into humans as well, right around the same time. So I was right around when I was sort of trying to think about what I wanted to do with my life. And I liked math, and I was not great at biology at the time. And so I decided, I heard statistics on the news about infectious diseases spreading. So I figured, heck, I'll try studying math and seeing if I can get into that area. And so again, I sort of like focused on mainly respiratory pathogens for much of my work. So during the COVID pandemic, it was a natural transition to work on COVID modeling. So I did do quite a bit of COVID modeling. I think that the impact of models during the pandemic has been really mixed. And I think that they've been super helpful, absolutely critical in many areas, and also not very useful, sometimes even detrimental in others. I think that, it's, a model is worthless, but a good model is worth the world in a way. So part of it is, and part of what we as a field are trying to do right now is to take stock of like what makes a good model and what types of questions are really answerable by models. So one of the things that I think has been really challenging with COVID and with infectious disease modeling in general is that there's a lot of interest in forecasting, and our ability to forecast epidemics is way behind our ability to forecast things like the weather. We would like to get to that point, but there are a lot of reasons why, you might even be able to think of why forecasting epidemics is incredibly difficult. One of them is data availability. One of them is that humans are a lot harder to predict than water molecules. And so we're really sort of lagging behind in that. But one of the areas that models has been really helpful is in this sort of scenario modeling, trying to help policymakers understand like what's the spectrum of possibilities and how do we hedge against the worst case scenario. Models have been super helpful in that kind of thing. So it's mixed, but something we're trying to actively do is figure out how do we do this better.
All right. Thank you so much for a detailed answer.
Yeah, thanks. I see a couple questions I'll field in the chat, and then maybe we can return to some in-person ones. So there's a question about can some of these questions be reduced to Markov chains and studying their properties? Yeah, absolutely. So depending on the question we have in mind, a Markov model can be a very good way of approaching that. So we use Markov chain models. We use differential equation-based models. So sometimes one of the challenging things with Markov chain models is that to reduce an infectious disease system to something that obeys the Markov property, where only the previous time step affects what's happening in the future, it can be very difficult to do. You can sort of reduce anything to a Markov model, but the question is how much pain do you want to go through to do that? Because there are some situations where history is hugely important, right? This is where immunity comes in. And so accounting for a person's prior immunity, for their strain-specific immunity, can cause things to very quickly deviate from that Markov property. And so your state space expands like crazy to actually bring it back into a Markov-type framework. So sometimes we do need other types of mathematical tools to approach those kinds of problems. But you're absolutely right that Markov chain type models are sort of one of the bread and butter type techniques that we use all the time. There's also a question of, is the model that we were talking about for multiple diseases, or is each model for a specific disease? So kind of depends how general you want to be. So the SIR model, so thinking about people as susceptible, infectious, and recovered, goes a long way for many different types of infectious diseases. I think that they're probably best used for things like respiratory infections that can be spread to casual contacts, if you will. And the reason I say that is that a lot of the work in sexually transmitted infections, for example, really need to take careful account of how sexual partnerships happen between people. And those are very non-random. And so understanding human behavior and really explicitly encoding that into the model is super important for those kinds of infections. It's also true for vector-borne illnesses, where rather than just tracking susceptible, infectious, and recovered people, you often also have to account for the ecology of the host, whether it's a mosquito or a mouse or a worm. And so oftentimes you end up with SIR type model for the people, but then also other types of models, or maybe even similar models for the vectors as well. So in some ways, what I presented today was sort of the simplest base case scenario that can do a good job of modeling many different types of infections. But the more you are curious about a specific disease, the more you really want to tailor the model to that specific type of infection. So I hope that addressed that question. If not, feel free to follow up. And the last one in the chat that I see at the moment is, so a question, when the susceptible population plateaus, does that mean most of the population has attained herd immunity? So herd immunity is a concept that sort of exists at the population level. So herd immunity doesn't belong to an individual. Herd immunity belongs to a population. So basically, when the susceptible population plateaus, essentially what has happened is that there is a high enough fraction of people in the population who have achieved immunity, who are basically no longer able to get infected and therefore are no longer able to spread infection to others, that those people are protecting other people from getting infected because they're running into immune people rather than potentially infectious people. So, so essentially, you're right. That's an interesting question. Does it have to be most of the population? So like, is it true that you need more than 50% of the population to attain that kind of immunity? I don't think so. I think that you can have, no, I think that is the case. I think that is the case that to achieve herd immunity, you need at least half of the population to be immune. And then how much more than half you need depends on the infectiousness of the pathogen. So that herd immunity threshold, the proportion of the population that needs to be immune from infection, increases with how infectious the disease is, of course. But that's the idea. You do need most of the population to be immune, and then how much more than half depends on the pathogen. Cool. What else? Yeah. All right. Cool. So deep learning, a machine learning type of technique. You're absolutely right. So there are a lot of groups, and ours is thinking about getting into this. We haven't much yet, but thinking about using machine learning, artificial intelligence type approaches to think about the spread of infectious diseases. One of the reasons that I have not delved into that realm too much is because one of my main interests is in mechanistic modeling. So basically in developing mathematical models where the terms of the model have a clear biological interpretation. And so one of the values of that type of modeling is that you can then start asking if-then type questions of like, if we were to increase the vaccination rate, or if we were to, if the disease were to evolve to become 1.5 times more infectious, or if the interactions between age groups were to shift because schools were closed, how would that affect the transmission dynamics? And to answer those types of very specific if-then questions, you either need a lot of historical data where those same interventions have happened, and then you can train a machine learning model on those data, or you need a mechanistic model to try to explore that space. With infectious diseases, again, like I mentioned, one of the key limitations is that there really is this gap in the amount of data that's available. We're racing to change that. We're really collecting a lot of data, but as it stands, we don't really have the historical time series to train machine learning type models on in order to answer some of these very specific policy type questions, unfortunately. Now, there are other areas where machine learning can be hugely helpful, including anticipating where an outbreak might emerge, or trying to understand sort of like where in the world an outbreak will spread to. So it's definitely been very successfully used in some contexts, but there are others where it's much less useful than a more mechanistic type of framework. So we focused more on the mechanistic side of things, and that's really what I presented today. But like I said, our lab is starting to get into some of the machine learning type aspects a little bit more for some very specific questions. Yeah, if you're interested in those types of things, I'd be happy to talk about that more.
Hi, I actually had a question. Yeah, so what is the kind of data you work with? Is it just solid numbers, or do you have like say like comma separated values of different kind of conditions that you take into consideration when you're making compartment models?
Yeah. So it's all sorts of things.
Okay.
So probably the most common type of data that we work with is what we call case count data. And so it's like numbers of hospitalizations, numbers of symptomatic cases, mortality over time. But there's all sorts of other things that I think are really interesting. So one of the things that we've done is looked at, of all things, medical insurance claims records. So every time you go to the doctor, that generates a insurance claim. And from that, you can extract a diagnosis and you can get a very good sense of what types of things people were infected with over time. We use, we've done a lot of mobility tracking. So there's like RFID and geospatial data that we use an awful lot. We've also done a lot of work with within host viral kinetics. So thinking about the volume or the concentration of virus in a person's nasal passages over time. You like take a PCR test, and by amplifying the PCR, you can see how much virus they were producing. And you can generate mathematical models just like you do for the population. You can generate those for how much virus is in the body over time. So we use those types of data too, which effectively end up, I mean, everything can be represented as a CSV at the end of the day, but it just depends on how complex you want your CSV to be. So we use all those different types of data and more. So basically, everything is on the table.
Gotcha. Yeah. Thank you so much.
Thanks. Anything else in these last few seconds? Cool. Well, it was wonderful to meet you all. Thank you for your questions. My information is all on the CU Boulder website. I will also post my email address here. Oh, without the I. That's the one. So feel free to reach out anytime if you have any follow-up questions or you're interested in the group, or you're interested in CU. But yeah, otherwise, thanks so much for coming. I'm excited that you all are interested in this kind of stuff. And yeah, hope to talk to some of you again soon. All right. Take care, everyone. Bye.